Okay, last part of chemical kinetics. Like I said, I'm going to save the KEQ and the Le Chatelier's thermodynamic part for the last unit since there's so much in this one. All right, so they talk about reaction mechanisms. Another way we can determine the rate law is to take a look at the step by step process under which a reaction occurs. Now, do understand some reactions do occur by a one step process. However, the more particles that are involved and the more complicated the structures, the more likely it is that it's going to take multiple steps before we get to our final product. And that step by step process is called a reaction mechanism. So, for instance, let's say we had a reaction between, and I'm going to use a certain program, so I'm going to make the atoms certain colors. Let's call the blue atoms B and red atoms R and the yellow atoms Y. And let's say our net reaction. Net reaction only has two things in it. It's got reactants and it's got products. And normally when we look at a net reaction, it's what we call a balanced chemical equation. All right, so in our net reaction, let's say we're trying to do, pardon me, 2 particles of red plus 2 particles of Y plus a mole of B. And that's going to give us the product R2Y2B. Now, the mechanism for this, the step-by-step process might be, well, in the first step, an atom of R and an atom of R come together and make a molecule of diatomic R. And then maybe in the second step, we have that product reacts with blue and gives us R2B. And then in the third step, maybe an atom of Y comes together with an atom of Y, and we get diatomic molecular Y. And then in our final step, we take the product from step 2 and react it with the product in step 3, and we get our overall product. Okay. So, a couple things. We said that what is in white is our net reaction. This is our balanced chemical equation. That's what we normally see, but that this reaction occurs in 4 steps. Now, a little terminology for you. If something is created in a step as a product, but then later it's consumed in another step, we call that thing a reaction intermediate. Now notice something, that reaction intermediates do not show up in a balanced net equation. And the reason why is because, one, they're created in a step and then they're later consumed, so they're gone. But they tend to be unstable materials that only exist for a few microseconds before they're consumed by a later step. So in this particular mechanism, there's a number of reaction intermediates. We would not put the product from step 1 in our net equation because it's consumed in step 2. And the same thing with the product from step 2 is later consumed in step 4. And the product from step 3 is later consumed in step 4 as well. So in our balanced equation, what you have are your original reactants, 2 moles of R, 2 moles of Y, and a mole of B, and those things show up in your balanced equation. And then the only product we have is the product from step 4, which shows up in our balanced equation as well. So net equation is our balanced overall chemical reaction, and then the steps create reaction intermediates that are consumed in later steps, and it is a step-by-step pathway to get to our final product. So the question becomes, well, why? Why does that happen, and why is that necessary? Well, remember we said that for our activated complex, right, E sub A, how much energy we need to get over the activated complex and then start to produce products. Well, particles have to come together, right time, right place, correct angle, on a functional group with enough energy to break bonds in order for that collision to be successful. So what are the odds of more than two particles coming together at the same time, same place, correct angle, blah, 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 blah? It's actually very slim. So what I have here is I have 16 particles of red and 16 particles of yellow and 16 particles of blue for our last reaction. Remember, we need two reds, two yellows, and a blue to come together all at the same time, same place, correct angle, blah, 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 plop, plop, plop. And I'm running this right now at 300K, which is a little bit above room temperature, not much. So if we stop this at any time, are we getting those sort of collisions? You know, we're close to a collision between, in the top center, between blue and yellow, and in the right center between red and blue, and in the bottom left between red and red. Let's try again, and boom. Now we have a collision between red and blue. I can see a collision between blue and yellow. I can see a collision about to happen among two blue particles. Notice a trend here. Two blues, a blue and a yellow and a red. I'm not seeing three or more particles come together at the same time, same place, correct angle on the functional group, although that can happen and does happen from time to time. It's just a very rare particle physics occurrence. So what if we add some more heat, get the particles going faster, get some more collisions here? So let's bring this up to 700 Kelvin, and we hit pause, and I only have a collision there at the bottom between red and blue, so we run it again, and we hit pause, and again, I'm not getting any collisions here with three or more particles. Really close on one. I got two blues and a yellow there in the left center. So it can happen from time to time. But again, what are the odds that five particles are going to come together and they're going to be the same exact five particles that we need? It's rare. So what happens is two particles will come together and form one. And then that one particle will hit another and they'll clump together and form one. So again, we go back to our mechanism. Step one, we're taking two particles of R and we're creating one molecule. Then we're taking that molecule and we're adding on another particle and turning it into one big particle. So that's really what we're doing step by step, is that we are taking collisions that involve maybe one, two, or even three particles and bringing them together to make one or two particles and simplifying our process. All right, so how do you get rate law from that? Which step is the rate determining step in a mechanism? Well, just like anything else, what determines the overall speed of something is going to be the process that takes the longest. Things that involve bond rearrangement, especially those covalent reactions that have complex materials like fats, proteins, carbohydrates, RNA, DNA, those sort of things are very slow processes because it usually involves some sort of change in shape that we're waiting for. So the thing that we're waiting for, the thing that takes the longest, is the rate determining step. Okay, so what does that look like then on a test? Well, suppose we go back to our original example here. Let's clean this up a little bit. Oopsie poopsie, cleaned it up too much. Looks like I could have just rewrote it quicker than I'm cleaning it up. Ugh. All right, so let's rewrite this then. R plus R gave me diatomic R. Diatomic R gives me that product, and then my final product. Okay, so suppose the first process takes 1 second, and the second process takes 1/100th of a second, and then the third process takes 426 hours, and that's ridiculous, but you know, some things do take a long time. Probably not 426. Let's go 42.6 hours, and then the fourth step, let's say that takes 1 microsecond. Okay, so when we add up the total time is 42.6 hours. And we're not going to add in that 1.010001 seconds. Nobody says 42, like 6/10 of an hour is 36 minutes. Nobody's going to say 42 hours, 36 minutes, and 1.010001. Nobody does that. So we're going to just say 42 hours, 36 minutes, which means that our rate is determined based upon what happens here in the third step. So we would say that the third step, which is the slow step, so our slow step is our rate determining step. Now, the rate law is based upon what's happening in the rate determining step. And we take a look at what's called the molecularity of the rate determining step. In this case, it involves two particles of Y. And so when we write the rate law, we would say that this is bimolecular, meaning two particles, two molecules, bimolecular, with respect to step 3. So our rate law is going to be rate is equal to K for step 3, although people don't usually write the step as a subscript. Just write K. K is equal to, rate is equal to K times concentration of Y squared. So it goes by the number of particles in the rate determining step. There were two particles of Y involved in the collision on the reactant side, and so that becomes Y squared. So when we say Y squared, that means bimolecular with respect to Y. Now I'm going to give you a little of disclaimer here. When I first started teaching this, I wasn't too concerned about this, but now that I've taught AP for a while and I see that it created problems, I've tried to change it over the last 10 years, but you'll see some of the old practice materials, I ignore this. When you write a rate law, it has to be in terms of something that is a reactant from your net equation. In this case, particle Y. That's a reactant, so we can write it in our rate law. And some of my other ones, you'll see a reaction intermediate used in the rate law. You can go with that for now, and then in AP Chem, we're going to teach you how to get rid of that reaction intermediate, because you can't define the speed of a reaction in terms of something you can't control. And remember that a reaction intermediate is something that's created, and it's highly energetic, unstable, in one step of the reaction and later consumed. So it's created by the reaction. It's not something you can go out to a chemical store and say, hey, give me some of this reaction intermediate. It's a highly unstable material that only exists for a few microseconds. But like I said, we'll take care of that on the AP level. All right, so what would I want from a test? A couple things conceptually. Let's take a look at molecularity. Okay. There are really 4 orders that make up almost all chemical reactions. There's 0 order kinetics, first order kinetics, second order, and third order. And the kinetics are determined by the rate determining step. Now, some reactions are only one step. So their balanced equation is also the rate determining equation. But for the most part, that's not all that common. When we talk about collisions, do understand collisions always involve more than one particle. So in this definition, for instance, first order kinetics are unimolecular collisions. Now, that doesn't mean that there's only one molecule in the collision. What it means is that we're waiting for something to happen with that one molecule before we can get a reaction. In other words, it's that one molecule that determines the speed. We can bombard it with other particles, and it's not going to change the speed of the reaction, because it's that one molecule that we're waiting for something to happen to, maybe a bond rearrangement, a change of shape, before the reaction can proceed. So in other words, the speed of the reaction is based upon what's happening with this one molecule. So we would say unimolecular reactions tend to rely on, all right, what's happening to one molecule. So we're going to just say that that's going to rely on bond rearrangement. Bond rearrangement for one molecule, and that means we are waiting for something to happen. Waiting for perhaps a change in shape. Okay. If the rate determining step involves 2 molecules that where both of them have an impact on the speed, then we're going to call that bimolecular in nature. Now, the reason why 2 molecules can have an effect on the speed is that in a process where bond forming and bond breaking occurs at the same time, in concert with each other, all right, happening at the same time, then you have to have both of those molecules for that to happen. So bimolecular collisions are things that involve bond breaking and new bonds forming at the same time. I'm going to write in concert. Bond breaking and bond forming occurs in concert with each other. I'm going to explain that in just a moment. So we need two molecules. The thing that is attacking and the thing that gets attacked. That would be a bimolecular collision. Now, ternmolecular would involve three molecules at the same time. Now, that's rare, unless maybe one of the molecules is a catalyst. I'm going to put a question mark there because it doesn't always have to be a catalyst. But if it's a catalyst, then remember that catalyst is going to do that fitting shape with two different molecules and bring them together. Maybe one molecule here and maybe one molecule here. So now we have all three of these molecules coming together in that induced fit model. Go back. All right, so we said with catalysis, we could have an induced fit. And if that's the case, then we need all three molecules. The catalyst, which I'm going to color in here white, that is going to attract the two reactants, the one in green and the one in red. And so you're going to have all three things come together at the same time. So that would be a ternmolecular collision. If it was four things, it would be quadmolecular and then quintmolecular. Again, more than two is rare unless you have a catalyst. More than three is extremely rare. So we're just going to focus on three types of collisions there: unimolecular, bimolecular, and ternmolecular. Now for zero order kinetics, and I explained this I think in the last video, or previous video, two before with catalysts. Zero order means that none of the molecules, none of those collisions affect the speed. And I said an analogy would be, suppose we had a room full of students and they needed to exit the room quickly. How fast they can get out of the room isn't dependent upon the concentration of students per se. It's more dependent upon the size of the door opening. So doubling the amount of students in a room doesn't make them get out twice as fast. We know that from common sense. In fact, it's going to be at least twice as slow. And with people jamming in together, it's probably going to make it even slower than twice as slow. It's the size of the door opening. That would be zero order kinetics. And a good example of that would be things like a surface catalyst. The size of the surface determines the speed of the reaction. All right, so what does it look like on a test? Well, they may diagram it. So here's some pictures of what we're talking about. The first one, A, this is actually a bimolecular collision. And what this represents is that you have this red particle and then you have this molecule that consists of two atoms of blue. Now here's my bond breaking. I'm going to draw that line for breaking. And then here's my bond forming, and they're occurring at the same time during the transition complex. So bond breaking and bond forming happening in unison means bimolecular, which means second order kinetics. For B, now we're looking at unimolecular. Now they show one particle. It doesn't have to be one particle, but what happens in a unimolecular reaction is that we're waiting for something to happen that changed for this particle, and then it can break apart. And in the third, the blue maybe represents a catalyst. And then this winds up being ternary. Not ternary, I'm sorry, I'm thinking proteins here for a second. That doesn't happen. Not ternary. Ternmolecular. Molecular collision. Okay, and so in terms of diagrams, they might say, well, here's a bunch of particle diagrams, reactants, transition state products, which one represents unimolecular? And you would select B. Another thing that they might show is if we go to our little diagram here with our tetrahedral complex, we said for tetrahedron, you have these charge clouds with the things that are attached to the central carbon, and they block on all four corners of the tetrahedron a particle coming in to try to make a collision with the central atom. It's not going to happen. They're repelled. So maybe our water solvent, water particles, for instance, have a polar end, so we have a positive end, negative end. Maybe this water solvent pulls off this chloride. And when it does, what you're left with are these three methyl groups. Remember, methane means one carbon. You have these three methyl groups, and so now the shape goes from tetrahedral to start, which is very stable, very unreactive. And now we go to trigonal planar. And since we're trigonal planar, we can attack it from the back of this without being repelled. We can attack it from the front without being repelled. We now have two sides where we get no electron cloud interference. This is an example of bimolecular. And what they're showing here is that maybe this purple is iodine, and then the rest of this is CH3, and this is going to be attracted again to a water molecule, positive end, negative end, and iodine is very electronegative. So, that would be, unimolecular if the water molecule was involved. We don't need the water molecule for this, it's bimolecular, As this particle approaches, notice, these things that are attached to the central carbon are facing to the left. But as this approaches, we have negative charge clouds. So what does it do when it gets near the negative charge clouds on that molecule? They repel. So what happens is, as they repel, these three things get pushed into a pseudo-trigonal planar position. And now that they're in that pseudo-trigonal planar position, their negative charge clouds are getting near the negative charge cloud on that iodine, and they're repelling each other. Now this center here is highly electropositive, and it's being attracted to the negative charge clouds. So you have bond forming and bond breaking at the same time, that the attacking particle is causing a shape change in the particle that gets attacked, the CH3I, that gets attacked. That's causing the three hydrogens to shift position, and then those three hydrogens are repelling the iodine and pushing it off at the same time. Notice in the final product, all the hydrogens in the third picture are now to the right side instead of pointing to the left side. And that repels the iodine and breaks the bond. So you have bond forming and bond breaking occurring at the same time. Okay. So what do you need to do on a test? All right, suppose I gave you the following mechanism. Let's do 2A plus B produces this nonsense in step 1. And then let's do particle C plus particle C produces this. And then let's do step 3, and then let's do step 4. Okay. I want you to do two things. One, give me the overall net equation. 2, what is the rate law? Now you need some information for the rate law. Let's say that this is the, let's make this first step the slow step and come up with the rate law. So those two things, give me a net equation, give me a rate law, and I'll pause it and I'll come right back to check on you. Okay, I'm back. All right, so here's how we do this one. As far as the net equation, we're getting rid of reaction intermediates. If it's created in the first step and then consumed as a reactant in the fourth step, we cancel it out. If it's created in the second step and then consumed in the third step, we cancel it out. If it's created in the third step, but then later consumed in the fourth step, we cancel it out. So what are we left with? 2 particles of A plus another particle of A. So that's 3 moles of A plus chemical B plus 2 moles of C produces these 2 products. All right, so there's my balanced equation. And then the second part of it, what is the rate law? So on the rate law, we focus on the molecularity, what's going on with the reactants of the slow step. We have 2 particles of A, 1 particle of B. That's a total of 3 particles. So this has to be third order overall. So rate is equal to K times 2 particles of A. So we're going to make that A squared. And 1 particle of B, so that is B to the first. And there you go. All right, now, in terms of what's going to be on the test, I didn't prepare properly, so give me a moment. We'll go to Edmodo, and we will pull up the test review, apparently pretty slowly. Okay, well, a lot of videos, taking a long time, big chapter. All right, here we go, chapter 22, and notes, update, test review practice. Okay, here we go. 1, distinguish between thermodynamic stability and kinetic stability. So again, just conceptual in terms of multiple choice questions. As a general trend, remember this is just a trend, doesn't mean all 14 million chemicals follow these rules, which tend to be exothermic, which tend to be endothermic. All right, thermodynamically stable tend to be endothermic, thermodynamically unstable tend to be exothermic. In terms of kinetic stability, again, kinetics has nothing to do with thermodynamics, so we can't say. It depends upon the nature of the activated complex. The more difficult it is to form the activated complex, the slower the reaction is going to be, which tend to be spontaneous. Well, spontaneity depends upon where you are in the universe, because spontaneity depends upon 3 things. And I'm going to put those 3 things on there, the delta G, delta H, and delta S. It depends upon Gibbs free energy, thermal environment, enthalpy and entropy. But exothermic tends to be more spontaneous than endothermic, at least at the type of temperatures that we have on our planet, lower temperatures. List and describe the 5 factors and which phase is affected by pressure changes. We know it's gas phase. Why are changes in pressure treated the same way changes in concentration? Because again, it's the number of collisions per second that we're looking at, and if we're decreasing the distance between particles by increasing the pressure, then we're getting more collisions per second. So again, the 5 factors: nature of the reactants, the temperature, concentration, surface area, presence of a catalyst, again, all in terms of particle collisions. So 3, again, the 2 different types of heterogeneous, homogeneous inhibitors as a 3rd type of chemical, and then going back to that energy diagram and knowing the parts of the energy diagram, being able to recognize which one represents a catalyzed reaction and which one's not. The definitions and concepts of unimolecular, bimolecular, termomolecular in terms of particle collisions, and recognizing them in terms of the diagrams. Use the rate determining step of a mechanism to determine the rate law. Write a net balanced equation. We just did that. Differential rate, number 6. Yeah, it's going to be multiple choice, but I may go with like 5 answers on it because I don't want people reverse engineering the problem when they take the test. But instead of FRQ on this, of course, it has to be multiple choice, but I'll definitely have at least 1 or 2 of those differential rate calculations on there. And then number 7, 8, 9, and 10. All that Le Chatelier stuff and KEQ stuff we're going to do in the next chapter. All right, so study hard, make everybody proud, and thank you very much.